Hello, and welcome to the lecture on 4.4. Today we're going to talk about the laws of logarithms. Now, first, I want to remind you of what logarithms are. So remember how a logarithm is defined. So y is equal to a to the x if and only if log base a of y is equal to x. Now, I want you to notice here, first and foremost, a logarithm is the inverse operation of an exponential. And then secondly, what I want you to notice is that x is equal to this logarithm. So this logarithm is this x value, which is an exponent on an exponential. So we want to think about logarithms as an exponent. It'll help you to understand logarithms faster if you think of them as exponents themselves. All right, let's get right into the laws. Laws of logarithms. Let a be a positive number with a not equal to 1. Let a, b, and c be any real numbers where a is greater than 0 and b is greater than 0. Then the following rules apply. 1. Log base a of a times b is equal to log base a of a plus log base a of b. Now, when I go through the proof, I'll explain how this works, but if you think about the logarithm as an exponent, then this should make sense. When you multiply two things together with the same base, you add their respective exponents. 2. Log base a of a divided by b is equal to log base a of a minus log base a of b. This is actually the exact same property as 1, except division means that you subtract exponents instead. 3. Log base a of a to the c power is equal to c times log base a of a. All right, now this third one, again, when you take something with an exponent to another exponent, you multiply those two exponents. Here c is an exponent, and then log base a of a is an exponent, so we would be multiplying the two exponents. Now let's get into the proof, and hopefully the idea that logarithms are exponents will make a little bit more sense here. Proof. I would recommend watching the proofs of these, even if you don't really care about proofs in general, even if you don't plan on continuing mathematics in the future. I think that these particular proofs are helpful to understanding logarithms. So 1, let log base a of a equal some value u, and the same thing, log base a of b equal a value v instead. Now remember what this implies. From above here, we have that a log base a of y is equal to x if and only if y is equal to a to the x. So we pattern match. A, the base on the logarithm, to x is equal to the y. So here we have exactly that. So I'm going to take my a to the u power is equal to capital A here. So a to the u is equal to a, and a to the v is equal to b. Then what we do is log base a of a times b is equal to, well, I have my a here and my b here. This will become log base a of a to the u times a to the v. Now what happens when we multiply these two things together? We have the same base, we have different exponents, so we add these exponents. And we get log base a of a to the u plus v. As you can see, this logarithm will mean a to some power equals a to the u plus v. That power is obviously u plus v. Because u plus v is the power on a, and that's the power we're looking for to put on a here. Now we resubstitute our u and v. So our u is log base a of a, and v is log base a of b. This. So we see that the log base a of a times b is equal to log base a of a plus the log base a of b. Now again, we think of u and v as exponents because they are exponents here. Now when you see your a, your capital A times your capital B, and they multiply here, we're adding the respective exponents. And then we simplify a little bit and we get this. Basically, if we have two things with the same base and we multiply them, then we add their respective exponents. 2. Log base a of a over b equals log base a of a to the u divided by a to the v, which is then equal to log base a of a to the u minus v, which is equal to u minus v. We just follow the same steps that we had here, because if we're dividing two things with the same base, then we subtract their respective exponents, so u minus a. And then a to the u minus v is equal to a to the u minus v power. Basically, if we didn't know what this was, we would be asking ourselves, a to what power gives me a to the u minus v power? So it has to be u minus v. And then again, we resubstitute. U is equal to log base a of a, and v is equal to log base a of b. And lastly, number 3, log base a of a to the c power is equal to log base a of a to the u to the c power. Remember, a is equal to a to the u power. So I'm replacing my a with a to the u. And now you might see that we have something with an exponent to another exponent. This is where we're multiplying. So we end up with log base a of a to the cu, which is going to equal c times u, because a to what power gives me a to the c times u power? Has to be c times u. And then we resubstitute our u, which is log base a of a. Hopefully this shows you that logarithms are nothing more than exponents. Let's do an example here. Evaluate log base 6 of 4 plus log base 6 of 9. So how would we do this? Well, we go back to the previous properties and see what we can do when we have an addition of logarithms. Here we have log base a of a plus the log base a of b, where our base is the same a. So we go back to our example here, and we have the base is 6. So our lowercase a in this case is 6. Our uppercase a would be 4, and our uppercase b is 9. So we can rewrite this as log base 6 of 4 plus log base 6 of 9 is equal to log base 6 of 36. And then we just need to figure out what that is. What is log base 6 of 36? Now again, this means 6 to what power gives me 36? Another way of thinking about this, if you think about it as an exponent, is what power do I need to apply to the number 6 to get 36? What power do I need to apply to the number 6 to get 36? And that number is 2. So this just equals 2. All right, try one now. Evaluate log base 2 of 160 minus log base 2 of 5. The next thing I want to talk about is expanding and combining logarithmic expressions. Okay, this subsection is just going to be using these 3 properties here. If we're multiplying as an input for a logarithm, we can separate it into a sum of logarithms. If we're dividing as an input of a logarithm, we can expand that into a difference of two logarithms. If we take a value to a power as an input of a logarithm, then we take that power and multiply by the logarithm itself. Do an example here. So what we want to do is expand log base 3 of x y to the second power divided by z. So notice that we're dividing by c and we're multiplying here. Everything in the numerator is multiplication. Everything in the denominator is division. So we have x times y squared divided by z. If we do this just one step at a time, we can look at the division first. And this will be log base 3 of xy squared minus log base 3 of z. Noticing that z is the only thing in the denominator, so we subtract that thing that's in the denominator. We then are going to expand out our first logarithm here because we have a product. So we get log base 3 of x plus log base 3 of y squared minus log base 3 of z. We're just carrying down the log base 3 of z here. And the last thing we do is we use property 3. We have y to the second power as an input of a logarithm, so I can take this power down to the front of the logarithm. So we end up with log base 3 of x plus 2 log base 3 of y minus log base 3 of z. And that's our final expansion. Try one now. Expand log base 2 of a squared times the square root of b divided by c times d cubed. Now be careful here. C and d cubed are in the denominator, which means we're dividing by both of these things. So be careful. There's a common mistake that happens with students here where you add the d cubed for some reason. You're going to end up subtracting this logarithm. Do one more example here. Combining logarithms. A log base 3 of x plus 1 plus log base 3 of z minus 1. We're going to figure out what this is equal to. And then b log base 2 of x plus 1 minus 1/2 log base 2 of x squared plus 1. We figure out what this is equal to. So for part A, we have the same base, so we can combine them. Since we have this same base, we can combine these two logarithms. We have a sum in between, which means we combine them into an input of a single logarithm. So we're going to have log base 3 of something, of the combination of these. Now, because we're adding, we multiply the two inputs. So we get x plus 1 times z minus 1, just like this. And that's it. You can't do anything more than this. Now notice here, this is not two different logarithms. A lot of times students will take this and write it as log base 3 of x plus 1 times log base 3 of z minus 1. This is not correct. We have a sum here between the logarithms. Now this sum between the logarithms means we have a single logarithm with the product of the respective inputs. So we have a sum of log base a of a plus the log base a of b. We take those inputs and multiply them and use it as an input for a single logarithm here. Notice here that we have two different logarithms. That's why this is not correct. B. Log base 2 of x plus 1 minus 1/2 log base 2 of x squared plus 1. Okay, so there's a couple of steps to this one. First, we have this 1/2 in front of the log base 2. We have to deal with this first. So remember what 1/2 is as a power. This is going to move up to be a power on the x squared plus 1. So we have log base 2, x plus 1, plus minus log base 2 of x squared plus 1 to the 1/2 power. And we have to write this in as an input to our logarithm. So this 1/2, remember, is a square root. So we rewrite this as log base 2 of x plus 1 minus log base 2 of the square root of x squared plus 1. Now this does not simplify. You cannot distribute this 1/2 over a sum, which means that we take the square root of the entire sum, not each one individually. Right? Now we're ready for this subtraction, to deal with this subtraction here. We have log base 2 of x plus 1, log base 2 of the square root of x squared plus 1. We have the same base, which means we can actually combine these. We have a subtraction, which means we divide as an input. So it'll be log base 2 of x plus 1, the positive term, divided by the negative term. We have this negative here. Square root of x squared plus 1. And we're done. This is the most combined version of the logarithm. Now I'm going to make a note here. First note, log base a of x plus y is not equal to log base a of x plus log base a of y. We have a sum here. We cannot expand that. You can expand a product. If we have a product, we can expand it into a sum of logs, but not if we have a sum. Okay, so these two things are not equal. Number 2, log base a of x divided by log base a of y is not equal to log base a of x divided by y. These are two separate logarithms. Yes, they have the same base, but they are separate logarithms, so they are not the same. We cannot go from this to this. This, log base a of x over y as an input, is log base a of a minus log base a of b. We would subtract their inputs. This is equal to log base a of x minus log base a of y. These are very common mistakes, so students mess these up. This is not equal to this. This is actually equal to this. You have to be careful. Third note, log base a of x cubed is not equal to 3 log base a of x. Notice here, this cube means we take the logarithm first and then cube it. We take the logarithm of x and then we cube the result. This is different. This is equal to log base a of x cubed. So we take our input value x, we cube the input, and then we take the logarithm. Order of operations matters. These two things are very different. So you have to be very careful. And you also have to be very careful when you write your logarithms. So if you write it like this, log base a of x cubed, this technically means this. Many times, students will write it incorrectly without the brackets, and they'll think it means this. It's not the same thing. If you use brackets, then this is the same thing as this. So you have to be very careful. The last thing I want to talk about is the change of base formula. I sometimes refer to this as the fourth logarithmic property. It's not technically the fourth logarithmic property, but it is a very nice and useful tool to have when you're moving on in mathematics. And everyone needs to know this when they're learning logarithms. Start with just writing out the change of base formula. Log base b of x is equal to log base a of x divided by log base a of b. So notice, for our logarithm, we have a log base b to start, and we have a log base a to end. So we're changing our b into a log base a. Now, what you do is you take your x, your input, it goes here, so we have log base a of x, but what this is it's a scaling factor. Because b and a are different, you're going to have a different slope on your curve here. What this does is it fixes that slope. It fixes that rate of change. Now I'm going to show you a proof of this, and this one you should be able to follow along with. We start by letting b to the y equal x, and this is true if and only if y is equal to log base b of x. Now, you should get used to being able to translate between these two different forms about saying the same thing, because these two are the same statement, they're just written differently. We do this a lot. We use whichever form benefits us the most at the time we need it. So let's start here. Log base a of x. And see what we can do. So log base a of x will give us log base a of b to the y, because x is equal to b to the y. So I'm going to replace my x with b to the y. And I end up with log base a of b to the y. Now, as we've noted before, with the third rule of logarithms, we can drop this down, this exponent. It's on the interior of the input of the logarithm, so we have b to the y as an input, which means this y can come down. So we then get log base a of x is equal to y times log base a of b. Then all we need to do is divide by log base a of b here. And we have log base a of x divided by log base a of b is equal to y. Now notice here that our y is equal to log base b of x, so I can replace my y with log base b of x. And we have now log base a of x divided by log base a of b is equal to log base b of x. What this means is that if we have a base that's not really beneficial to us, we can change that base to something that is more beneficial. Something that will help us to simplify the expression a little bit better. And let's do an example for this. Find log base 8 of 128. 128 is not a multiple of 8, so I can't just say that this is going to be equal to some number, some integer value. So instead, what I'm going to do is replace my 8. I'm going to change my base from 8 to 2, because 128 is a power of 2. It's 2 to the 7th. So what I'm going to do here now is say use this formula, log base b of x is equal to log base a of x divided by log base a of b. So in our case, we're changing from 8 into 2, log base 2. So my b is going to be 8, my a is going to be 2. And then you pattern match this. So my b is 8, log base 8, my x is 128, is going to be log base 2, because my a is 2, my x is 128, as I said before, and my b is 8. So we have log base 2 of 8 here. This one is efficient because 8 is a power of 2, and so is 128. So actually, both of these will resolve really nicely. So we end up with, then, log base 2 of 128, as I said before, was 7, and log base 2 of 8 is 3. So we have log base 8 of 128 is 7 over 3. Now again, this comes out nicely because 8 is a power of 2, and so is 128. Both of them are a power of 2. If we didn't have that, then it won't come out as nice, and you'll have logarithms that are in your solution. Like, for instance, this. This is usually what happens. But suppose we want to find log base 7 of 36. I can change my base to be a 6 because it'll simplify the 36 very nicely. So I want to do that. Log base 6 of 36 divided by log base 6 of 7. The change of base formula. Now this does not resolve. This is in simplified form. This is as simple as it goes. But log base 6 of 36 is 2. So this will be equal to 1 divided by log base 6 of 7 times 2. Which you can write the 2 in the numerator as well. But this is actually relatively common to have a logarithm like this in your answer. All right, that's going to be it for today. I will see you all at the next lecture.